the emergency gets notified by either manual or automatic activation of what is called a beacon. And this beacon is like equivalent of what we would do if we are in some kind of emergency. We would shout, help, 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 save me, save me, save me. So it's this beacon that's supposed to say that for you in electronic form for the whole world to know, so that you can be saved. Now there are various standards at which this works, and the standard on which we have worked is what is called a 406 megahertz band beacon, which is universally available across the world. So it's expected that a ship or an aircraft that is facing some kind of emergency activates this beacon, and this beacon sends out a signal periodically to the satellites that are listening. To be sure, GEO is not the only constellation of satellites listening. There are LEO satellites, which are low Earth orbit, and there are MEO satellites, which are medium Earth orbit. And India has a play in this entire range, and I think we should all be very proud that ISRO is really contributing to the entire world's search and rescue efforts to these segments. So this signal goes to the satellite. Satellite acts like a bent pipe. It sends a signal down. Only thing, while doing that, it changes its frequency. From 406 megahertz, it changes it to something like 4.3 gigahertz to C-band, and then it sends it down. Now you must understand that when it is receiving an alert, it can receive all the way from South Africa to Australia. But when it is sending it down, it doesn't have to go all the way. It only has to go to the listening station. And this is the reason this frequency translation is done. So at the higher frequency, you have more directivity, and for the same tiny amount of power that is available on a satellite, you can actually direct it to the precise listening station, which happens to be in Bangalore. So the signal goes there. And this is where our work begins. And why is this challenging? Why am I taking 45 minutes of this Transtech 20 to tell you this is an important instrument? It's challenging because the signal has to go all the way to 36,000 kilometers to start with. And the beacon that is there either on a boat or a ship or an aircraft, or even a fishing boat, a small fishing boat, cannot really be a very sophisticated beacon. If a fishing boat is going to carry it, it can't be very expensive. It can't be having a huge power source. It can't be sending hundreds of watts of electric power. So it's typically these instruments are very small in size. I show you a bunch of these beacons in this slide, and some of them in fact fit in a pocket. So the power that you send out is relatively small, and this low power or weak signal is to go all the way to 36,000 kilometers, and the bent pipe sends it down. It has to come back, and then I'm going to decode it. And I think you know that the 1 over r square rule that plagues all engineering, right? If I do something here, its impact seen at a distance r is always 1 over r square, right? So because of that, the signal, when it has traveled so many kilometers and come back, it becomes extremely weak. It's completely ridden with noise. And from that kind of noisy signal, the challenge is to know who this is, where is this, what kind of emergency is this, so that the search and rescue effort can be directed to that location. So this is the challenge. And I must say that this challenge could not be solved in the old days. There was nothing like this before digital communication started, because the signals are really extremely weak. And it's the digital signal processing that we employ in all our implementations that makes it possible to decode this signal and get the location, the identity, etc. Of whoever is in distress completely identified. So I'm not going to go too much into technical details, but I still want to tell you how these things work at the top level, how this equipment looks, and then we'll probably look at a few examples of the use, or where this was really used, how it has helped, and so on. So this is digital communication, and digital communication means bits and bytes, right? You all have a digital ID. Your digital ID, most common digital ID is your cell phone number, right? It's a number. It's a 10-digit combination of actual numbers. You know? So this can be represented in bits, and then it becomes a fixed thing that cannot be changed. If it was analog, that means it was a function of time that would continuously change, then noise can alter it. But an ID, which is based on numbers, it cannot be altered, right? And this is the reason the beacon technology also uses a message format based on digital techniques. And the message format, a typical message format is what I'm showing you here. So this has different fields. Some of you would have worked on computers and looked at protocols like TCP/IP and things like that. And you know that all that is framed, and each frame has certain bits allocated for something, certain bits allocated for something else, and so on. So likewise, this also carries a preset structure. And this structure is decided by the international body COSPAS-SARSAT. So it's got features that allow you to lock on the signal. It has got features that have identity of the party. It has features that even give the location of the party. And for this, the beacon is supposed to have what is called a GPS, a Global Positioning System receiver. Once you have a GPS receiver, you have lat long of that party, and this information gets encoded in this format. So it's sufficient to know that this is a very tiny amount of information. You can't write a story in this message. You can only give very tiny amount of information. I think to be precise, it's about 144 bits. And all the information that you want to put about the distress is encoded in this and is put in the message stream. This message stream has some features. If I'm sending it up in the air and expect that it echoes down and somebody receives it, I want to maximize the chance of its getting identified, then I must be building in features which will prevent any kind of misidentity or miscommunication. And this is called, in our digital communication terminology, we call this forward error correction. That means I anticipate that there will be errors in my communication, and I build in features in my message so that those errors will be spotted. It's little like one simple example I can give you is, if in my message bit stream I count all the number of ones, and let's say this number is 20, and I put it at the end of my message stream, and on the received signal if I don't get 20, then I know that some communication error happened. And this is the simplest way. This is called a CRC check. Of course, this science also has evolved a lot, and there are